we want to talk today about air resistance, and then I want to generalize to show you why I've said to you all, I'm not going to give you a specific equation, you're going to derive the equations yourself. First of all, what is air resistance? How many of you have ever stuck your hand out of the window of a moving vehicle and first of all done this and then done the air surfing trick where you kind of change the angle of your hand? Okay, so hopefully all of you have felt air resistance. It's a really tricky force. If I actually want to calculate a general formula for air resistance, it depends on a bunch of things. First of all, as you go faster, what happens to the force of air resistance? Okay, so in the equation for calculating air resistance, there's a V, actually a V squared, it turns out. What happens when you expose less of your hand to the wind? Does the force get bigger or smaller? So it also depends on the cross-sectional area of the object moving through it. There's a capital A in the equation. It also depends on how dense what you're moving through is. So water resistance is bigger than air resistance because water is more dense than air. The symbol for density is the Greek letter rho, and so there's a rho in the equation. There's also a drag coefficient. It's a really complicated equation, and we're not going to get into it that way. What we are going to say, Ashley, is with Newton's laws, we can find the air resistance at a given point. So what is air resistance? Well, it's the force of air molecules bumping into an object that's moving through the air. And here's the key. What direction is air resistance? It always has direction opposite to motion. So in your free body diagram, if they ask you to include air resistance, which way are we moving? Point the arrow in the opposite direction. Is that okay, Nick? Okay. We're going to draw free body diagrams for 3 situations in example 1. A ball being thrown, so situation A is while it's in my hand and on the way up. Situation B is after it's left my hand, but on the way up, right there. And situation C is after it's reached the top and is on its way down, right there. But now it wants me to include air resistance. Okay, I'll zoom in on the first diagram. While it's in my hand, while I'm throwing it, what are the forces acting on it? Oh, wait a minute. Did they give me a picture? Rather than do a completely separate free body diagram, I'm going to be lazy and just label my picture. Is that okay? So, Kate, what are the forces acting on it? Get the obvious one. Definitely. Watch. While it's in my hand, which way is the ball accelerating? So which way must there be a bigger arrow? Yes? How do I know there has to be a bigger arrow up? Watch. I'll show you when the arrow isn't bigger than gravity. My hand is wide open. The ball moved up, but did you notice it didn't leave my hand? For it to leave my hand, arrow has to be bigger pointing up. Otherwise, I'm not going anywhere. Is that okay? What force is that? You could call it a normal force, I guess, if you wanted to treat my hand as a surface. I'm actually going to make up a new name. I'm going to call it F throw, because that is to me what it is. It's how hard I'm throwing it. But I do have to be stronger than gravity. Otherwise, it's not going to leave my hand. That's not the interesting free body diagram. That was just to kind of jog your memory for practice. I'm much more interested in diagram B. Jan, which way is the ball moving in picture B? Up. Okay. What are the forces acting on it? Get the obvious one. Okay. What else does part B want me to include? What does it say in the instructions? To include what, Jan? Which way is air resistance? Which way is the ball moving? Air resistance is always the opposite direction of motion. So which way is air resistance? Which way is the ball moving? Air resistance is always the opposite direction of motion. So which way is air resistance? I'll give you a hint. It's the opposite of up. Yeah. I'm going to put it right beside I'm not quite sure whether air resistance is bigger, smaller, or the same size, because air resistance can change. I think I'm going to assume that we've just started to go down, and so air resistance is smaller. There's really, if you made that arrow bigger in this question, I couldn't take marks off because we don't know. Hey, Zach, what about in situation C? Okay, now we're on the way down, and it says include air resistance. What are the forces? Get the obvious one. Okay, you're starting to see why I encourage you to do gravity first. It kind of gives you a thing to hook everything else into. Okay, go systematically. Don't rush to the ones you're uncertain of. They'll become much more obvious. So gravity, I agree. Which way? Up, bigger, smaller, or the same size? I'm gonna gamble. I think smaller. Can air resistance ever be bigger than gravity? That's a good question. Let's come back to that. I'll throw that out there as a Look at this middle diagram, example 1b. I wrote here in example 2 as kind of a thought puzzle. How can the ball be rising if all the forces acting on it are downwards? Isn't that impossible? Or is it? How can it be rising if all the forces are downwards? Yeah. There is no upwards force. You know how I know there's no upwards force? Because I have not drawn any arrows pointing up on my free body diagram. You were doing great until that. The first part, I was like, oh, yeah, but please, and I have to lovingly beat that out of you, there is no upwards force. First of all, which way is the ball traveling? Up. Is it speeding up or slowing down? So which way is it accelerating? Which way is the ball traveling? Up. Up. Can we say up? So which way is it accelerating? Not backwards, but down. Look at my free body diagram. Does that allow me to accelerate down? The key here to realize, again, is Newton's laws only tell us the direction of acceleration, not motion. Are we accelerating down? Yes or no? Yeah. Does that free body diagram make us accelerate down? I got no problem with that. So, we are accelerating backward, up and backward, down. Moving up but slowing down. I'm good with that. Example 3 says, if the falling ball in 1C is speeding up, if it's speeding up, which force is larger? Write an equation. Who's winning? Who's winning? Everyone except Reed. Gravity. Who's losing? Equals? There's our force equation. Winner minus loser equals ma. As far as I'm concerned, then, I can either give you A and say find F air. How would I get the F air by itself here? What's right in front of the F air that I don't like? I would do the swappy dance. I would plus the F air over and minus the MA over. Or I can give you F air and say find A. Nick, how do I get the A by itself? Divide by M. Okay. Oh, let's do one with, here we go, we got some numbers. Suppose the ball in example 2 has a mass of 2 kilograms. If air resistance is 5.2 newtons, what is the acceleration in, situation B? I've scrolled down. Take a look at situation B. See it? Who's winning? Who's winning? Who's winning? Who's winning? I'll give you a hint. If you just say gravity, you're wrong. It's a trick question. What? They're both winning. It's elementary school sports day. Everyone's a winner. Who's losing? What would losing be in situation B? What direction would the loser force be pointing? Is there any forces pointing up? All winners, no loser. So what does a winner mean? I put a plus sign in front of it because it's positive. So it's going to look like this. mg plus f air equals ma. There doesn't have to be a loser. There can't be in that one. Nick, how will I get the A by itself? Yoink. So let's plug in the numbers. A equals, Ashley, what's M? 2. What's G? Do I need to put the negative in? No, I took care of that with my setup. And then plus, not minus. Can you see how, by the way, if this was a multiple choice question, would I also have, if someone had gone minus F air? Oh, heck yeah. What's F air? Do I need to multiply that by 9.8? No, it's in newtons already. I'm good with that. This is a force. Divided by, what's M? I think I do that in my head. It's going to be 19.6 plus 5.2. It's going to be 24.6, 24.8. 24.8 divided by 12.4? Yeah. Try this on your own, please. And it's an acceleration, meters per second squared. Mr. Duke, that's bigger than 9.8. Yeah, this time, because not only is gravity slowing it down, air resistance is slowing it down, so the acceleration will be bigger than 9.8. Yes, it will be. Now we're being a bit more accurate with our free fall. Ooh, situation C. Lena, in situation C, who's winning? Who's losing? We do have one this time, I think, yes? Because there's an arrow pointing in the opposite direction. Okay, so what is it? mg minus f air, is that right? Equals ma? How would I get the A by itself? Nick's theorem? In fact, I'm noticing, Lena, that it's exactly the same as part 1, but instead of a plus sign, I just have a minus. You might be able to, if you've listened to your favorite physics teacher and bought a good calculator, you might be able to just backspace edit and change the plus to a minus, and you're good to go. Do you get that one in your head, Mr.? Well, okay, maybe I can. It's going to be 19.6, take away 5.2. It's going to be 19.6, it's going to be 14.6, 14.4, 7.2? Yeah. Meters per second squared. We're in free fall, but we're not getting the full 9.8 because air resistance is tugging against gravity, a little less than 9.8. Is that all right? So this is about what we can handle with air resistance. I'm not going to give you the air resistance equation with drag coefficient and calculate. I'm not going to do that. You really need calculus to do it properly. But we can do it in snapshots like this. I like example 4. I like example 4. Example 4 is a nice question. Partly because I've jumped out of it. Have I mentioned I jumped out of an airplane? Because I have jumped out of an airplane. Mr. Dewick, are you going to say that every time? Maybe. Parachutist free falls for a time and then opens a parachute. His new upward acceleration is 1.5 meters per second squared. Ooh, A says, why is his acceleration upwards? Why isn't it downwards? First of all, when he pulled the chute, which way was he? Oh, yeah, Zach.
He's slowing down?
Yes. First of all, which way was he traveling when he pulled the chute? Looking for where that starts with the letter D.
Down.
Once he pulls the chute, does he speed up or slow down? So if you're traveling down, but you're slowing down, which way are you accelerating? And that's all. Newton's laws only tell us the acceleration, not the motion part. Okay? So, good. Zach, let's keep going. What does part B want me to do? I'm going to do it kind of next to the parachute here. I could almost label the parachute, but I got some space right here. Okay. What are the forces acting on the skydiver? Get the obvious one. Yep. What else? Air resistance. Bigger, small. First of all, which way? Up. Bigger, smaller, or the same size as mg? And how do I know? Bigger, smaller, or the same size? How do I know? Can't be smaller. How do I know it has to be bigger? Which way are we accelerating? Which way must there be? You see, this is why Newton's first law is such a powerful tool. Which way are we accelerating? Which way must there be a bigger unbalanced force pointing? Gotta be. I'll exaggerate it so it catches my eye. So then read, what's my equation? Who's winning? Yep. Again, as far as I'm concerned, I can either give you the acceleration and say find the air resistance, or I can give you the air resistance and say find the acceleration. I think in the previous one, we found the acceleration. I'm willing to bet here they want us to find F. Oh yeah, D says find F air. Read, how would I get the F air by itself? Yeah, add, right? Plus the mg over. Is this a swappy dance? This is not a swappy dance because there's no negative in front of the F air. I'm happy with the way it looks. So I'm going to leave it where it is. And it's going to be MA plus MG. Read, what was M? Was it 90? What was A? Plus 90 times 9.8. Do that one in your head, Mr. Good. Maybe. Sure I can. It's going to be 90 times 11.3. So it's going to be 990 plus 27. So 1017? Yeah. Newtons. I can do math in my head. I can do math in my head. I factored out the 90, and then I went 1.5 plus 9.8 is 11.3, and I went 90 times 11.3. That I can do in my head. Anybody here jumped out of an airplane besides me? Have I mentioned that? The skydiving, the physics of skydiving, now that we're bringing in air resistance, is really quite lovely. First of all, air resistance is not a constant value. Air resistance would be maximum right when this person pulled their parachute. But eventually, air resistance gets smaller and smaller until eventually, Marcus, it exactly matches mg. We have a special name for when air resistance matches mg, gravity. Does anybody know what we call it? We call it something velocity. You've probably heard the term. See how I did that? You probably heard the term. Wasn't that smooth? Term. Yeah, terminal velocity. Terminal velocity is when gravity and air resistance are identical and you stop accelerating. Does that mean you're floating? No, it means you're not speeding up anymore. I've experienced two types of terminal velocity. Once when I was in free fall, and then I hit a second, much slower terminal velocity after I opened my parachute. So this next little bit, if you watch, this is a lovely video looking at the physics of skydiving. And in particular, I like that they're really emphasizing the forces. Hopefully, none of this is new. Hopefully, this is you saying, yep, I understand all that. But watch.
When a skydiver jumps out of a plane at 3,000 meters, her speed goes through some big changes. So what's happening to the forces as you fall through the air? The force of gravity is always trying to pull us towards the Earth.
What are the forces acting on her right now? Get the obvious one. Is she accelerating down? Is she accelerating up? So I know there's an arrow same size as gravity pointing up. What force? I'll give you a hint. She's sitting on a surface. No, she's sitting on a surface. This is normal force. Okay? In our free body diagram right now, it would be mg down, normal force up, and they're identical. When she jumps, which force is going to vanish? And now we'll have mg down.
Before the skydiver jumps, the floor of the plane provides a counterforce, which balances the downward force of gravity, right up until the moment she steps out.
What are the forces acting on her now? Get the obvious one. And then let's pretend she hasn't even started falling yet, so no air resistance, but as soon as she starts to move, there's going to be an arrow pointing up that's going to get larger and larger and larger and larger and larger until it exactly matches gravity. What I like about this, you're going to see, they're going to show the free fall speed in the bottom right corner, and you'll notice at the beginning it gets bigger really fast, but because her acceleration is decreasing, the speed changes slower and slower until it stops changing. Watch. So there's the speed in the bottom
Gravity
right corner.
immediately pulls her towards the ground, and she starts to accelerate downwards.
Okay.
But air resistance is acting in the
Watch how fast the numbers change. The changing numbers are going to slow down
opposite direction.
because we're getting more and more air resistance canceling out
The
gravity.
faster she falls, the greater the air resistance.
See it? Okay.
Eventually, the upward force of the air equals the downward force of gravity.
What do we call that? That's terminal velocity. For most people, it's around 50, 55 meters per second. Could you multiply that by 3.6? How many kilometers per hour? Really close to 200 kilometers per hour, which is a nice round number. Is it 198? Is that what you said? Would you want to hit the ground at that? No, so we better do something.
When forces are balanced, the speed remains constant. That doesn't mean she stopped falling. It means she stopped accelerating.
When she pulls her parachute, which force is going to get larger? Why must it? Because for her to survive, what does she need to do? Slow, which means she needs to accelerate which way? Up. Doesn't mean she's moving up. Just means she's going to slow down. So pull the
She's
parachute.
still doing a steady 55 meters per second, and hitting the ground at this speed isn't a good idea.
No.
To slow down, the upward force needs to be greater than the downward force. When the parachutes open, air resistance suddenly becomes much greater than gravity. The forces are no longer balanced, and this changes her speed.
See the
She
speed
slows
decreasing?
down.
But also, as she slows down, air resistance gets smaller. The speed isn't changing
Because
as
she's
fast.
slowing down, air resistance decreases until it balances gravity again, and she reaches a much slower constant speed. Approaching the ground at 5 meters per second is a much better idea.
Oh, when she hits the ground, which way will she accelerate, technically? Because the ground has to slow her down and bring her to a stop. Which one of those arrows will get bigger right on impact then? Normal force will be there again.
As she hits the ground, there's a thumping great counterforce from the Earth,
Normal
which
force.
decelerates her very quickly.
Is that okay? Some lovely physics going on there so that people can survive jumping out of an airplane. Have I mentioned that? Okay.
You have a video of it?
I do. There's one on YouTube, I think, if you do a search. Example 5. I like example 5. I like example 5. This is to let you know that the tools that I've given you, Newton's laws, a good free body diagram, winner minus loser, you can solve an awful lot with this. 5,500 kilogram helicopter accelerates upwards at 2.5 meters per second squared. Taryn, what does this want me to find? The what force? You know what this is a good job for? I think I'm going to do a free body diagram. Now, how did I know that? What does this want me to find? Lift force, that's one force. Is there also gravity? Probably. Is there more than one force? Time for a free body diagram. I'm going to do it over here on the left. Now, I'm not even sure where we're going to go, but I'm not going to panic. I'm going to go systematically. What are the forces acting on this helicopter, Taryn? Get the obvious one. Have you written something down? I feel better now, yes? Which way is this helicopter accelerating? Does the question tell me? Ah! Which way must I have a bigger arrow pointing then? Yep. Care to guess what force that is? I'll bet you that's the lift force. I'm going to call that F lift. If you were really lazy, you could call it FL. Uppercase L, because if you put a lowercase l, you'll think it's F1, which might confuse you, right? I've never done this before, but we can figure this out. Who's winning? Okay. Who's the loser? And she did it again. Wow. Jeez. Equals MA. I guess I would say now for this helicopter question, I could have it accelerate down or up, as far as I'm concerned, and I can either give you A and say find the lift force, or I can give you the lift force and say find A. What are we trying to find here? Oh, let's get F lift by itself. I guess add the mg. So it's going to be 5,500 times 2.5 plus 5,500 times 9.8.
You have that one in your head, Mr.
Well, maybe. It's going to be 5,500 times 12.3 times 12.3, Mr. Dewick? Yeah, times 12.3. So 5,500 times 12. Oh, I'm getting yucky numbers. No, I'm going to wimp out. I need a calculator. What do you get? Something in the 6,000s. No, 60,000s? Give it to me to read the digits. Six what? 67650? Yes. So I'm going to go to 3 sig fig. I'll go 677. I'll go. That's typically what I do in my answer keys, in case you're wondering. If you gave more digits, I won't take marks off. But if you're trying to see if you did it right, how come my answer's off by a bit? Maybe I just went to 3 sig figs and rounded off. By the way, what if this helicopter was accelerating down? What would the equation be? Can you get it from the free body diagram just by imagining the arrows changing? mg minus F lift equals ma. What if we're hovering? What would the equation be? What? F lift plus mg? That's not an equation. You didn't give me an equals anything. What if we're hovering? I don't, yes, but no. No. What if we're hovering? What? What's 0? If we're hovering, are we accelerating? So the forces must be? I'm looking for a word that starts with letter B. How about mg equals F lift? They're the same. I'm pretty sure that's the only 3 situations I can throw at you. We're either accelerating up, down, or not at all.
Backward?
No. It's vertical. Example 6. A rocket which weighs 12,740 newtons on Earth is launched. The force of propulsion is 15,400. Okay. Ooh. Ah. Keegan, what does A want me to find? Huh? Didn't they give you the mass? Isn't it 12,740? What are the units next to that 12,740, Keegan? Do I measure mass in newtons? What did they give me there? I think this is mg. How do I find m if I know mg, the weight? No, now. Divide by 9.8. Oh, so you're telling me the mass is going to be 12,740 divided by 9.8. What do you get? $1,300 even? Units, Keegan? I measure mass in newtons? Kilograms. Verizon. B says the upward acceleration of the rocket. What does B want me to find? Do you see a VI or a VF or a T? You know what this might be a good job for? Keegan, what are the forces acting on this rocket? Get the obvious one. Which way? Okay. What else? I'll give you a hint. Read the question. Propulsion. I'll call it F prop. Bigger, smaller, or the same size as mg? I'll give you a hint. Read the question. Why? Okay, there's three things. Look up. It says upward, bigger. Wait a minute. They gave me the numbers. That's a bigger number. And launch. So yeah. Joink. I'll exaggerate it. I'll call it F prop. Keegan, what's my equation? Who's winning? So start with that. Yep. This is why I said to you at the beginning of this unit, Keegan, there's no way I can give you every single situation. I'm going to teach you how to derive it from scratch and Newton's laws and a good free body diagram. What are we trying to find here? Oh, how would I get F prop by itself? What are they asking me to find in part B? Okay, how am I going to get the A by itself? Yep. Nick's theorem. So we'll have A equals, now it's plug and chug. Complicated plug and chug, yes, but it's plug and chug. 15,400 minus 12,740 divided by 1,300. I don't think you're going to get, I think you're going to get something in the 2s or in the 3s. Double check me, but I don't think you're going to get a very big acceleration. But all of you should try typing this into your calculator. Otherwise, how will you know if you know how to type it? Gershine, what'd you get? So 2.05? Anybody else? I don't see any nods. I see 2 nods, 3 nods. I see a thumbs up. That's good NASA speak. Keegan, acceleration units. Yep. Hey, let's go to the moon. Raj, what's part C want me to find? Okay, where? What location? We've moved the rocket to the... Yeah. You know what this is a good job for? Free body diagram. I know, you've been away. We're welcoming you back. We missed you. You should have heard what he said when you were gone. Terrible. He told us your nickname. Oh, okay. What are the forces acting on it? Get the obvious one. Oh, where are we? What planet? Or what space object? The moon. So I'm worried I'm going to put the 9.8 in because I'm dumb that way. So here's what I'm going to do. I'm going to go MG, and I'm going to put a little moon as a subscript just so I don't do something silly. Because it would be easy later on to be typing the numbers and put a 9.8 in by habit. Yes? Easy to prevent. What else? Oh, the force of propulsion. Bigger, smaller, or the same size as MG moon? Which way does this question say we're accelerating? Which way must there be a bigger unbalanced force pointing? Same answer. Who's winning? Minus mg moon equals MA. In fact, really, this is the same as part B, but instead of asking you to find A, what did you say they're asking us to find, Raj? How would I get F prop by itself? How I move mg moon over? Yep. So the force of propulsion is going to be ma plus mg moon. It's going to be m, which was 1300, times a. No. Times a is 3.5, Mr. Dewick. Plus m, which is 1300, times g on the moon, which is 1.6. This is actually way more accurate than A or B, because there, on the Earth, we would, in real life, in real rocket science, you do have to include air resistance. Do you have to include air resistance on the moon?
No.
Ooh. Easier. Raj, what'd you get?
Do you have this one in your head, Mr.
Well, maybe. It's going to be 1300 times 5.1. 1300 times 5 is going to be 6500 plus 130. 6500, 6600, 6630? Am I right? Yeah. Units, it's a force. Newtons. Okay? So these two examples, I like them both. I'm purely trying to let you know, Eric, I can be pretty flexible with what I can handle here. We don't always need to do a free body diagram. When don't I need to do a free body diagram? There's a trigger phrase that's worth kind of committing to memory. Dan, if you look at example 7, what's example 7 asking me to find? The what force? The what force? The what force? Everybody, the what force? Everybody, what force? If it ever says the net force, you can go straight to F equals ma. That's physics code for, I've done the free body diagram already. The numbers that you're getting are after we've done our winners and losers. So what does this want us to find? The what force? I can go straight to F equals ma. As far as I'm concerned, if I give you a net force question, Dan, how many variables are there in this equation? I can give you any two, find the third. So I could say find m, that would be, how would you get the m by itself? How you move the a over? Yep, F over A equals M. I could give you F and M and say find A, Nick's theorem, or I can give you MA. In this case, MA, what's M? Yep. What's A? What are the units next to that 33? Do I measure acceleration in meters per second, Verizon boy? So I'm going to, and this is not to make fun of you, this is to help all of us. That's a bad guess. Okay? What are the units next to that 8.5? Do I measure acceleration in seconds? So you ready? Do I know A? That's why I like this question. A little bit of a, okay. By the way, if this was multiple choice, would one of the answers be putting in the 33? Yes. Would one of the answers be putting the 8.5? Yes. What do we need to find? Even though this question technically said find F net, you know where we spend most of our time finding? What is that 33? Not A. Okay, what's that 8.5? What are the units right next to it? Yep. What are the units next to that 33? What do I measure in meters per second? Distance? A football field is 100 meters per second long? Okay. It's okay. You kind of jumped into this a bit late. You joined us a bit later. What? I think it, what is it, folks? Which one? VF or VI? What's VI then? How do you know that? Okay, Dan, we also should have underlined, we should have systematically right? Done that either mentally or actually. So I could say, hey, VI is your, I bet you if you'd done that, your brain would have said, there must be a V. There is the VF. You would have got there. I'm looking for an equation, Dan, that has an A, a T, a VI, and a VF in it. There is one. Those are all still totally fair game. Why? Because F equals M what? Well, there's a bunch of ways to find that A. Which one? Get the A by itself, please. So, you're right. Okay. Is it VF minus VI over T? I'm going to be lazy. I'm not actually going to find A. I'm going to say M times VF minus VI over D. There's yet another equation for force. It's not just MA, it's M bracket VF minus VI over T. Am I going to memorize that one? No. Am I going to write that on my green sheet? I don't think so. I can handle it. And I'm going to go straight to plugging in numbers. So M was 1200. I am going to ask you to type this in. I'm coming back to you, Dan, so make sure you're ready, okay? VF is 33. What was VI? Does minus 0 make a difference? Over 8.5. So it's going to be 1200 times 33 divided by 8.5. Which is what? Sorry? 4659? I'm going to go 4660. Because I tend to go to 3 sig figs. And it's a force. I said I was going to come back to you. I didn't, but you got the same answer, right? Good. Okay. This is going to sound weird, but have I really taught you anything new today? I kind of hope not. I hope it was more, well, yeah, I'd noticed some things about air resistance when I stuck my hand out the window. Okay, you've clarified it. So, nerd trivia, not on your test. Everything that I've just taught you is a lie. There are only 4 fundamental forces in all of physics. Normal force doesn't exist. Tension does not exist. Friction does not exist. Propulsion, no. There are only 4. What are the 4? There's something called the strong force. That's what holds the nucleus together. Because the nucleus is full of protons and like charges repel. Without the strong force, nuclei would fly apart. They would explode. The strong force, though, only acts over, it's very strong. That's why we call it the strong force, but it only acts over very, very, very tiny distances. How tiny? About the size of a nucleus, tiny. So, tiny. There's also something called the weak force. How do you think the weak force compares to the strong force? Any guesses? It's weaker. What's that? That's also acting in the atomic nucleus. That's what explains radioactivity and particle decay. Okay. Then there's gravity. Although you might recall from special relativity, I talked about general relativity, and I said some physicists would say gravity is not a force, it's a curvature of space-time. And then there's electromagnetism, which explains everything else. So pretty much all the forces that I'm doing with you are some variation of that 4th one. But we're not going to dive down to that quantum level every single time. It's just confusing. Okay? I wanted to go on a big rant, and I will, but I'm going to do it on another day because this lesson has gone a bit longer. It says power break. First of all, we already watched the inertia video. That was the big rock globe that floated on a little thing of water at in West Vancouver. I've showed you that. I will go on my power bracelet rant. Who are my basketball players here this year? Okay. I'll tell you how about 10 years ago some of the players were not very smart, and how they got scammed, and I'll show you how the scam is run. But that's another time. I can show you the physics behind it. For now, I'm just going to get you started on the homework, and unfortunately, you need to practice this. There's going to be a lot of homework, so you're ready. Here we go. 1, 2, 3. Or 1, 2, 3. Ectotin. 1, 2, 3. 1, 2, 3. 4, 5, 6. 7. You can skip number 8. But you can do number 9, or as I like to say, yeah, 9. Right? 10 is good, 11 is good, 12 is good, 13, 14, 15, 16 is good. So really, pretty much, I think it was just skip 8. But I wanted to give you about 15 minutes. You do have 15 minutes to work on this. The last half is mostly conceptual and should go fairly quick. But the first one, I've got you doing elevator questions for lots of elevator questions. I've got you doing air resistance for practice. It's good practice. The remainder of class is yours. Thank you for your patience.